past the boot phase to where the operating system is then can call these services to shut down. There's very few runtime services actually to be able to do a reset of the system correctly, resetting all the buses and the CPU and getting the time and date and access certain NVM variables and things that the OS needs in order to be able to boot the system, whether it's for security or other purposes, but to be able to change the boot options for the OS basically. So the up on the left-hand side, the legacy OS loader, that's referring to is during the change between the legacy BIOS and UEFIs, we provided a driver or a way of running the legacy BIOS. So internally at Intel, we've actually been using the UEFI, or what we call the Tiano Core BIOS model for many, many years. We've already switched to using the core base, code base that UEFI has been developed on, and we have this driver that's actually a legacy BIOS, the standard calls that you recognize in 18, 13, 10, etc. And that's what's been booting your operating system for these past probably 4 or 5 years. So there's other specifications like ACPIS and BIOS. Those things don't change at all, whether you're running legacy or UEFI. Those things are all the same. UEFI actually adopts or uses some of those other specifications in addition to PXE and some other specifications that we've absorbed into the UEFI specification and allow you to boot the operating system and run the operating system. So the whole object of UEFI is, off the UEFI system partition, is to be able to load your OS loader, your Grub2 or eLilo off of UEFI system partition and transfer control to the OS. And then your other OS partition, whether it's ext3 or 4 or NTFS if it's Windows, that's the portion of this that's not available to UEFI, and that's there for once your OS drivers come up and start running. That's the portion of the disk or the storage that the operating system is responsible for accessing and getting storage from. So all your runtime drivers and OS runtime drivers are expected to be part of your OS partition and not part of the UEFI system partition. So this is generally required to be what we call GPT, or gridded partition table format. That's a requirement for UEFI, and that's where these partitions are separated between the UEFI system partition, which is a FAT-based partition or a FAT formatted partition, and then the rest of the disk, which should be your OS partition, which is your ext3 or swap partition or whatever format your OS requires. So it's the job of your installer, when you install your operating system, to partition the disk correctly using this gridded partition table format, and then provide the UEFI system partition, as well as taking care of laying down the OS partition, ext3 or 4, and formatting it in the correct format. In addition to the storage on the system, there's typically other plug-in cards or other chips on the motherboard that might be used in, and if there's any services, boot services or console services that you need in pre-boot or the loader phase, the option ROM or the UEFI driver for that card should be provided by the silicon vendor. So the BIOS vendor provides the common what we call architectural protocols and drivers that all UEFI systems need to provide, and then the individual silicon provider, whether it's Intel or Broadcom or LSI or whoever the chip vendor is, needs to provide that bottom level driver, UEFI driver, for the particular storage or console or network device that you'd use. So just a little bit of history here. Unfortunately, there's 3 or 4 versions of UEFI that have come out since the very beginning, since the original. It's actually before 2006, the original version of Itanium that came out, which was the early UEFI 1.02. So since then, Intel's given up the specification to a forum called the UEFI org, basically. And so I have this little shirt, there's a little red logo on here. So it's a set of 12 companies which are the promoters, and they the UEFI org is a nonprofit organization just like USB and PCI that owns the IP for UEFI. So most of the systems shipping out there today, if you pick up an average motherboard or a server or desktop motherboard, may have lurking somewhere in the BIOS, probably UEFI 2.1, somewhere between 2006 and 2007. There's something called EDK 1117 or something that in the lower right-hand corner that your BIOS vendor may talk about. That's somewhere in between UEFI 2.0 and 2.1, but because none of the operating systems except for Itanium require UEFI, it's probably hidden in there, and there's a variable amount of interoperability you'll find with the UEFI implementation. I think other than Windows 7, I don't think there were too many people that were actually implementing UEFI or seriously using it to actually boot their system. It wasn't until late 2010 Microsoft decided to make it a requirement for Windows 8. C, which has a bunch of small modifications made by the various BIOS vendors and Microsoft and Intel on the implementation that you'll see in most systems that will ship in this time frame in the end of 2013. So from a silicon standpoint, if you've been watching, for Intel, if you've been watching our releases, it's really the Ivy Bridge timeframe that we're starting to ship systems with UEFI 231C. Probably by the end of the year, you should see BIOSes that appear on production boards that should be shipping in aligned with the Windows 8 shipments that are coming out here soon. So those are the UEFI specifications above, and that talks about the version of the protocols and drivers and handlers that you should have. BIOS or in your flash BIOS for your system. There's something called Shell 2.0. There's a newer version of the UEFI shell which replaces DOS. So if a vendor chooses to include the shell, mostly only in larger systems or larger flash like a server would have a shell in there. And then there's a packaging specification which talks about PI 1.1 or 1.2, which is the drivers that the silicon vendor provides for access to the flash and other things that are internal services to UEFI, between UEFI and the chipset and the processor that are there for silicon vendors to solidify on. There's a specification called the PI spec, the platform innovation spec, that allows the silicon vendors to solidify on the driver model. For UEFI and what the OS loader uses, we have something called the DXE drivers. Those are the driver execution drivers, and that's what the silicon vendors like the Broadcom or Intel Network, LAD Division, or LSI, that's the specification that they should be paying attention to. And there's a document called the Driver's Writer's Guide that they can take a look at up on UEFI.org, which allows them to work through the driver model that they need for their particular hardware device. UEFI follows a self-certification test similar to USB, where in the middle layer here there's a self-certified test that you can run from the UEFI shell that are up on the UEFI.org site. So you can go up to, there's one for 2.1 in 2009 that we released, and one that right now for 2.3.1 that is in the final stages that you can now download from the UEFI.org. So if you want to check to see if your particular BIOS in your system actually is compliant with the UEFI specification, you can go download from UEFI.org the SCT, the self-certification test, that will tell you if the protocols even exist, if the drivers and protocols even exist on your platform, and do they have the correct arguments. It's designed to be an existence test, not a functionality test, so it depends on what your particular operating system or implementation actually uses. Will depend, your mileage will vary depending on that. So there's a lot of thrash. In 2007 and 2008, there were a lot of people that BIOS vendors that did not do a very good job of implementing their UEFI and including all the correct architectural protocols and drivers. So remains to be seen here in 2012 or 13 timeframe whether or not they've succeeded in pulling everything in correctly and passing that. For implementation, the lower box here, there's a website called channelcore.org, and that is our open source website. There's a project that you can go to, and that will have the actual source for all the core of UEFI, what we call the architectural protocols, and the base drivers for the Intel, the base PC architecture. You still need drivers for the specific CPU and chipset that you're running on for your particular hardware, and that would come from your BIOS vendor or from Intel or whoever your OEM BIOS provider is. So not everything is open source, but the bulk of the common code between all the different systems is open source and available on channelcore.org. So down at the very bottom are the labels here that up on channelcore.org and the EDK2 project, there's these labels called UDK 2010, and if you wanted to go to the SVN, you can see there's UDK 2010 SR1, UP1, that's the UEFI 2.3.1 and PI 1.2 label that is up there for the open source. So if you're a driver writer for UEFI, that's the place you would go to pull the code down and write your particular driver. So that's what this slide is explaining here, the versions of UEFI and the things that the BIOS vendors and the driver card vendors need to do in order for them to write code that is compliant with the UEFI specification. So the way the UEFI org is organized is there's different working groups. There's one group. The main group for the specification is the UEFI. The top one is the UEFI USWG. So my understanding is Philip is working with the legal team at SUSE to make sure the SUSE as a corporation and employees can participate as a contributor. So there's 3 different levels of participation. Adopters, which anybody can be an adopter and go to the UEFI.org and download the spec and the code from tianacore.org and implement it and adopt it. To contribute back to the open source project, you have to give up the IP, and that requires signing a contributor's license. So as once that passes through the lawyers and that gets signed, then you're able to contribute back to the UEFI source code, the actual implementation on tianacore.org, and it's under a FreeBSD license, so there's no unlike GPL, there's no requirement for end producers, OEMs or ODMs, to hand the source code back. So that allows people to do their own particular implementations and not worry about any IP or patent infringement. The UEFI shell specification, which we're up to level 2.0 right now, that has its own working group and its own source code up on tianacore.org and its own spec on UEFI.org. The PI specification is for the silicon vendors. That's the Intels, AMDs, etc. For us to work on and its own specification. UTWG is the group that works on the SCTs. So there's a working group that writes tests and makes sure the self-certification tests pass, and your particular BIOS implementation will, if you run that test, you can figure out whether your particular motherboard or notebook actually abides by the UEFI spec. And then there's the PI distribution package specification. That's really for silicon vendors to worry about whether their drivers are packaged for the BIOS vendors correctly or not. So these are all the different groups. There's also a marketing group that announces things like the UEFI Plug Fest, and I believe the next one is in Taiwan in Q1 of 2013. So that'll be the next official Plug Fest for UEFI, and hopefully everyone will be there to try out their systems. This is just a basic execution flow from reset as to what's going on in your system if you have a UEFI BIOS. There's the SEC phase, what we call the security phase, where when we come out of flash and you come out of the reset vector, the process will go through and verify that the packages in the early pre-EFI initialization phase before memory comes up, that all the packages have been decompressed correctly and the processor and chipset modules are as they should be when they come out of the flash. So the pre-EFI phase is the phase where there's no memory assignment. The memory controller has not been turned on yet, so the drivers are all designed to execute in place. After the pre-EFI phase, after we initialize the chipset, turn on, load the microcode, initialize the chipset, and find out how many memory DIMMs there are, and turn on and run out of flash and copy everything out of the flash. At that point, after the memory controller is initialized, then we can create a stack and a heap and now run C code basically. So we're able to then run the standard UEFI drivers that you would see in a BIOS and bring all the basic UEFI services up and running and get your boot device initialized. Then we go to the BDS phase, and it allows us then to look at the NVM variables, see which operating systems are installed on the system, and the boot manager is then responsible for analyzing what boot options there are and then load the appropriate OS loader, figure out which device it needs to boot off of, and then run the appropriate driver and then load the operating system loader off of there, and then transition to the OS loader. So the final phase, once the grub2 or the OS loader then loads the required loader off of the EFI system partition, it'll then start the kernel and other OS services, and then run something called exeboot services, which then erases all the EFI boot services from memory and then transitions to the EFI, the operating system memory map and the kernel, and then you're running the OS at that point. So then we call that runtime, OS runtime basically. There's a concept of what we call afterlife, and that is if the operating system crashes for any reason or decides to execute an exception, there are methods to go back to EFI that some high-end RAS servers use to try and start the system back, or at least put a log in place for error recovery. But we won't talk about that here. That's a more advanced topic. We won't fit in this discussion here. So for UEFI Secure Boot, we're going to talk about these phases from the SEC phase to the transient load, where the OS bootloader takes over, and then the OS runtime. We'll talk about that later on, how the Secure Boot works with this flow right here. This slide talks about all the different UEFI services. So if you're writing Grub2 or you're using UEFI DXE or boot services, the runtime service table and the variable services are critical for you to be able to understand how Secure Boot works and defining what options you want to set up for the operating system to come up and run. We won't go through all of this since we only have 2 hours, and most of you won't be writing the OS loader. The things you are concerned about is what devices that you will be booting off of. Typically, there's 2 phases for most devices or OSs. When you want to get your operating system, there's the install phase, and then there's your actual boot phase. Part of the new features with UEFI 2.3.1 is people are implementing something called fast boot. So a lot of the devices that are affected by fast boot are listed here. These are typical boot devices that people provide drivers for. So typically you're installing to the hard disk, and on a server it might be a RAID or a fiber channel device. Typically you're installing from some removable media, USB or CD-ROM or DVD-ROM, and there's a specific format, L3DO no emulation, or the fat partition off of a USB stick that you're typically installing from a specific location off of that removable storage device in order to get it onto the hard drive or RAID volume. For servers and other desktop systems, usually the BIOS will provide some PXE boot services if you want to be able to install from a PXE server. And also, if you're trying to install to an iSCSI or SAN device, we provide drivers to store on a server to be able to boot and run off of an iSCSI device. So for Future Media, there's quite a bit of work going on in that area. You've seen some of the Apple MacBook Pros, there's SSDs, and now non-volatile storage devices are coming out that will be extended in UEFI. So with the driver model in UEFI, you'll be able to if they include those drivers in your BIOS, you'll be able to talk to those newer devices, and something the BIOS vendors will obviously be extending, and Intel will be extending into the future beyond 2013. As a quick review here of a GPT, GUID partition table format. I know there's earlier versions of SUSE that did not have this implemented, and it was an earlier mistake in this distro that they didn't support GPT. They were actually installing MBR. So one thing you want to make sure of before you install your operating system on there, if you boot to the EFI removable media, whether it's USB or DVD, that you make sure that the partitioning utility actually lays down GPT, and there's a variety of reasons for that. One is the GUID used in the GUID partition table format identifies your particular disk. You can tell where it is in the system as in part of the device path. There's various serial GUIDs that identify the EFI system partition or ext4, so you know which partition is the ext4 partition, and MBR doesn't have that. So you'll find various implementations running around out there that and SUSE, unfortunately, is one of them that doesn't correctly identify the partition correctly because it was laid down as MBR instead of GPT. So there's all kinds of problems if you pick up the disk and move it around within the system that you'll run into if the disk isn't partitioned and formatted correctly. And it's the job of your installer, whether it's YAST or whatever the installer is, to correctly partition the disk and lay it out in GPT format. One of the advantages that you have is there's a limitation MBR of 2.2 terabytes, and a lot of the disks today, especially in server storage, go way beyond 2.2 terabytes. So for the boot partition or for the boot disk, you can go up to, I think it's 9.9 exabytes for your storage partition on there. So there's a lot of people that are, a lot of operating systems have already moved to this a long time ago, and it's important that you make sure your disk is formatted correctly in order for you to take advantage of the features in UEFI and the larger partition format. So the other slides here just talk about the advantages of using GPT over MBR, which is what DOS and the older operating systems have been using for years. I'm not going to go over all those items. The other things I'll jump to here, since we only have 2 hours, is to start on some of the secure boot services. One of the things I wanted to cover is the device path protocol and the storage protocol, since those are typically the protocols used when we boot to an operating system. So in one of the chapters, chapter 9 I believe, in the UEFI spec, it talks about the device path, and this is a data structure that we use to specify where we're booting to off of our storage, whether it's SATA or SSD or whatever it is. So you do need to understand how to read the data structure and how it's parsed and used, because as part of the things that we do in secure boot, we make sure this image at osloader.uefi is signed, and you'll need to understand some of the data structures here to be able to work with secure boot. So typically once, if you remember the earlier slide presentation, the job of the loader, the UEFI BIOS is to pull the grub2 or your OS loader off of a storage device and then transfer control to it. So the device path is the data structure that tells you where that partition is and where that OS loader image is at. So in the example that we have here, we're using the UEFI device path protocol, which is actually borrowing the ACPI PNP data structure designation, and we're using those as device nodes in this data structure to specify where exactly on the SATA partition that we're actually at in order to boot off of the osloader.uefi. And typically for SUSE, this would be ELILO or grub2, depending on which version of SUSE that you're installing or that you're executing off of. So this data structure would be stored in the NVRAM boot option for the particular NVRAM entry in a system once it's installed. And so this data structure would tell me exactly where the grub2 or the ELILO is on the hard drive. So in this particular case here, you see it's on PNP 0A03 is telling me it's on a root bus bridge, which is bus 0. That's what the second, after the comma, the second byte is. It's 1F1 is the specific PCI device, and where the SATA controller, and it's using the primary master controller of the SATA controller, and then this partition 3 is where the EFI system partition is, and it's in a directory called /EFI/boot/osloader.uefi. So that's the specific name of the file on the EFI system partition that we're going to transfer control to. So understanding how this is parsed by your BIOS and what's being stored in the NVRAM entry is critical for you to understand where you're going to boot to. So you should see several of these, and this is what YAST should install into the your NVRAM or flash in order to be able to boot to the operating system correctly. So picking up your hard drive, moving it around, obviously will have some consequences if you move it to a different channel, whatever, based on this device path here. We're not going to go through all the boot services. I don't think we'll have time to go through that. Most of your BIOS vendor should provide those boot services in order for you to be able to boot. One of the things that, as I mentioned before, at the very end of the OS bootloader, grub2, once it finishes pulling the EFI, the OS loader off of the EFI system partition, it will execute something called exeboot services, and so all of the EFI services, what we call boot services, will be erased from memory, and then only the runtime services basically reset, and the NVRAM rail services will be left. And at that point, the OS operating system kernel and driver should be running, and UEFI is no longer available at that point. So this is a typical design, and I don't think we'll go through here as far as all the different drivers. If you're a BIOS vendor, you'll need to know about how to write drivers for all the different devices for your particular implementation. So we'll skip over the driver model here for now. There's different versions of UEFI, as I mentioned. There is, unfortunately, the Linux community had not really had been testing the BIOSes out there, so unfortunately the earlier versions of UEFI 2.1, which is what you'll see on most commercial motherboards today, doesn't actually work with most versions of SUSE and the Linux distribution. So no one was paying attention to the memory services, and so most of the core BIOS releases didn't actually implement any of the EFI memory services correctly. And so that's why you'll see various versions of motherboards today. If you can find the UEFI boot feature when you say boot to the UEFI shell or to the device, you may find there's some issues with booting to SUSE/11 or a various version of Ubuntu or whatever. So the reason why is the memory services aren't actually working correctly in a lot of these distributions. So in UEFI 2.1, we've added several different features here for the card vendors. The HII and protocols is sort of a bytecode version of a browser that we included so that the setup engines for the plug-in card vendors could run these setup engines to set up the RAID or network or whatever and fill in the fields that you need. And there's a bunch of other driver features that the card vendors have to implement in order for you to be able to get to your storage device. So what's required is in purple here, and what's optional is in black. And this is really for your card vendors when you're communicating them to understand what is required and what is optional. In UEFI 2.2, we added IPv6. There's a request from various OEM vendors and OS vendors to include IPv6, and actually SUSE/11 SP1 was one of the first OSs to include support on the server side for having a PXE server that supports IPv6. And on servers, it's fairly important, since in most data centers you'll find that you'll run out of IPv4 addresses very quickly for all your storage arrays. So this was at the request of many data centers and large OEM, server OEMs basically. And this is where we started adding the security model for UEFI, having the driver signing and getting the OS trust relationship with the operating system going. So the initial version of UEFI 2.2 was incomplete. We had a good and bad list, and we'll talk about 2.3.1 to actually talk about what's actually implemented today in UEFI. 2.2, there was some additional driver model implementations. We still didn't actually finish. The USWG was still working on the security model and driver model for UEFI, and it wasn't until 2.3 or 2.3.1c that most people actually started implementing BIOSes and firmware. At the same time, 2.3 was specifically cut for ARM, so for the people that were interested in getting ARM to boot UEFI, they added a bunch of bindings specifically for their architecture and the protocol so they could boot off of UEFI. And then it was 2.3.1 that actually we finished that. The USWG group finished that in September of 2011 and published it, and then most of the BIOS vendors started implementing off of it. About the same time, Windows and Windows 8 and other vendors operating system vendors started working on UEFI and implementing to the specification. So we have an SCTs. If you go up to UEFI.org, you can run that and check to see if your particular implementation matches the UEFI 2.3.1 specification. And that's where there's a campaign started by Microsoft and some of the BIOS vendors to go out and make sure that people are implementing UEFI 2.3.1c and secure boot. And that's where a lot of the Linux community started waking up in the 2012 timeframe as to some of the things that were coming. So that's mostly what we're going to discuss here is the features that come with UEFI 2.3.1c and secure boot and some of the networking requirements. One of the changes was also added for secure encrypted storage. There's two specifications, an OPAL and IEEE 1667 specification, which allows us to pass through commands to a secure encrypted hard drive or a storage device. So some people have the requirement on notebooks to have the hard drive be encrypted so that if you lose the notebook that you can't read the data off the drive. So that was added in there in the 2.3.1 time frame, 2.3.1a. They added it to IPv6, the concept of a DWID, so that each system has its own unique device ID, so you can identify it on the network. It's similar. DHCP4 has a similar method as well for identifying systems on a network. And then for TCG, for the physical presence specification, that's part of the TPM, and they relaxed some items there, so for servers they didn't have to worry about actually proving physical presence on data center servers. So a lot of these improvements, USB 3.0 was added because that's when that hardware appeared, so there's a standard HCI driver, and some improvements to the IFR forms for the setup engines for plug-in cards were added. So the other feature is fast boot, and that's something that you'll see on most notebooks or ultrabooks that are coming from Intel. There's a Windows requirement that you have to boot in less than 2.4 seconds on SSD-based notebook devices if you want to get their certification. So some terminology here. Microsoft sort of designated that you need to have Class 2 systems. You need to turn off what we call the CSM, or the legacy BIOS. So it's been driving a lot of the requirements today for the BIOS vendors and OEM vendors to become Windows 8 compliant. So there's 3 different classes in the UEFI forum that they talk about. Class 0 and Class 1 are typically the systems you see out there today. They have something called the UEFI CSM, or the legacy BIOS. It's a driver that's written to one of our PI specifications that allows you to boot to the non-UEFI operating systems out there, so DOS or Windows XP or whatever, older versions of Linux. So starting from 2013 or end of 2012 here, we have Class 2, and there's a switch in the BIOS, or the default mode in which the BIOS boots today, and that is booting through this UEFI 231C mode as opposed to the legacy switch. And I've subdivided the Class 2s into 3 different cases, A, B, and C. One where you have the legacy BIOS, what we call the compatibility software module in UEFI 2.0 or 2.1, the older versions of UEFI. That's the current board you see out there today before the UEFI 231C. The Type B that basically had UEFI 2.0 or 2.1 lurking in the BIOS setup, but you have to go find that switch to turn it on. That may or may not be easy to find. And then there's there's Type C, which is what's being required by Windows 8, and that is where you turn off the CSM. It ships default in UEFI 231C mode, and you can only boot to a UEFI operating system. So C is what's required by Windows 8 logo. They have an additional requirement that if you're a client or, for example, a notebook or desktop system, that you in turn also turn on a secure boot, which requires you to sign both the OS loader and the UEFI drivers to make sure that you're only running approved, signed firmware, and you're not just running some random piece of malware or something that might be coming up through the system. Class 3 systems is where the CSM has been removed from the flash, BIOS flash, and you can no longer boot to what we call a legacy or non-UEFI OS. So there's people that want to save money and remove that from the flash. So in the future, when the older operating systems are no longer around, or you're not using those operating systems, then you might see Class 3 systems shipping out there. So systems or tablets or devices that are only booting Windows 8 or UEFI class operating system may be running Class 3 if they remove all the legacy BIOS out of the system. So explaining some of the requirements that Windows 8 is forcing upon various OEM hardware vendors and BIOS vendors to be able to certify and boot with Windows 8. When they say, it's Windows 8 certified, what that means is that the Windows 8 OS loader is going to install and use only the UEFI 231C boot and runtime services. So by default, those need to be enabled in your BIOS. So when your system comes shipped, from an OEM vendor or from, for example, Intel, this will be turned on by default, and you will not be able to boot any legacy operating system like Windows or Linux that is not UEFI enabled. So this is the right and left half of the screen here. So the right-hand side is how the BIOS is used to ship by default in legacy mode. You didn't see anything different. You drop your DVD in or USB stick, and you boot to your legacy OS, whether it's Windows or Linux or whatever, DOS or whatever it is. With that change occurring now at the end of 2012, early 2013, you're going to see the systems coming out where they're going to boot by default UEFI. So there's quite a few changes and requirements to the system BIOS. I've included the Microsoft published Windows 8 logo requirements in a document. There's an MSDN site. You can go to that link down there and you can see the full specification from Microsoft. It's a public specification on what are the UEFI requirements, firmware requirements that you have to have in your hardware and in your BIOS in order to meet those requirements. So most of the OEMs and BIOS vendors are shipping the systems obviously to be Windows 8 compliant. So that's what's driving a lot of the changes in the system, and you'll see those requirements for secure boot and other things in this document listed at the bottom here at that URL. One of the other features in Windows 8 that it's not a UEFI requirement, but it is a requirement for Windows 8 certification is what they call fast boot. They're taking advantage of booting to the left-hand side here by eliminating all the time that it takes to enumerate and run the legacy BIOS in the system. They've been able to prove on most UEFI 231C systems that post time can be cut down to less than 2 seconds, including the security and TPM support. And in their operating system, Hyper Resume and device init can be cut down to 4 or 5 seconds basically. So they're able to get up to their Windows, the login prompt basically inside of 5 or 6 seconds total. So on an SSD device without a TPM, if you grab an Intel Ultrabook or most systems I've seen, they're what you would call touch enabled. With Windows 8, I've seen most of those systems boot in less than 2 seconds. You're sitting there touching the screen and hitting applications and Windows apps and things within 2 seconds. The resume time without the CSM is typically when you do an S3 or an S4 resume is less than 4 seconds. And then device init, depending on your storage device, should take less than 2 seconds. That's part of the 2-second post time. So in their WCL or their Windows 8 logo requirements, even if there's a TPM or TPM 1.2 device in the system, they're only allotting about 300 milliseconds to do the security check of all the drivers, to see whether they're signed correctly or not. So there's a max time of about 2.3 to 2.4 seconds that you'll see on most of the Windows 8 enabled boot devices. So from my practical experience, having some of the early prototype devices lying around for people to use, once people see a system that boots in less than 2.5 seconds, they have a tendency never to use any of the older systems anymore. If you have tablets or notebooks around, they're not going to sit around for 2 or 3 minutes waiting for Linux or Windows to boot. Most people just don't have the patience anymore to, whether it's an Apple system or a legacy BIOS system to boot. So that's just from a practical standpoint what we've seen. End users, this is a very visible feature that they can see on the newer devices, that have a tendency not to want to use the older devices once they can do this. So it's an important feature, I think, that you should pay attention to if you're implementing a distro or an operating system that people are actually going to want to use. We'll talk about secure boot here, since there's quite a bit of stuff that's going on in this area. So I mentioned before, there's the UEFI 231 specification from UEFI.org that's got all the information that you'll need for secure boot. We're going to talk about the work going on here in the Linux community now to also implement this for Linux. So for secure boot, you need to sign the grub2 and image that that the BIOS is handing off to. There's a cryptographic signature or sign tool that Microsoft is using that we typically use when we sign the BIOS itself. There's a private key signing that Microsoft has decided to host as part of their CA services, and that's the shim loader that Matthew Garrett and the people in the Linux community are using to sign with the Microsoft CA or the UEFI CA. And then there's a public key in the platform that is also used for the platform to sign other images in there. I want to distinguish, there's something called, I've been talking about the TPM, and there's something called trusted boot, and that's a way of measuring everything that's been running in the system as you come up, and a way of filling out the PCR registers inside of a secure trusted platform module called the TPM. A lot of the notebooks and desktop systems have these modules, and operating systems such as Windows 8 and Windows 7 actually log what they're actually running all the way up through the operating system phase to figure out whether there's malware running or not. And we highly encourage people to actually utilize the TCG drivers and specifications and things that we use within UEFI and our BIOS as well. People choose sometimes not to implement that depending on whether they want to spend the money on the hardware or not, but that is something that you should pay attention to. There's a new NIST requirement that came out recently this year for these are security guidelines as part of a way of updating and what BIOS should be implementing in order, from a government standpoint, for security purposes. And they name specifically the TCG specification and the secure boot as a guideline that the government will look at when they're purchasing systems from various OEM vendors and which operating systems they're using. So the difference between what we call UEFI Secure Boot and the TCG Trusted Boot is UEFI Secure Boot is checking the signature of all the components before we actually transfer control to them. So between the UEFI firmware and the OS loader, we're going to check to see if the OS loader and the UEFI drivers are signed correctly and match the UEFI CA from Microsoft, whether they've been signed by that signing source before they transfer control, and it won't continue execution unless they are. And that's where a lot of the alerts went up in the Linux community, because a lot of the Linux code obviously is not signed. And then there's trusted boot, which is a way of measuring, not just checking to see whether I'm going to, run something that actually is signed, but also checking to see when I do run something that I measure that image, that PCOF image, from the flash or from the disk, and then putting the results of the hash of what I executed into a PCR register in a TPM. So one is talking about trusted boot. I'm actually going to measure and make sure that just because something is signed doesn't mean it isn't a piece of malware. So there's a way of recording what actually ran in the system and checking, and also taking advantage of some of the other secure areas in a TPM device where you can store keys and other things, and also a log to check what happened when a system came up and booted, and as opposed to just setting the policy of I'm going to only run signed images. So I just want to make sure people are distinguish between trusted boot attestation of what I'm doing when I boot, as opposed to just the UEFI secure boot that people are required by for Windows 8. This talks about the trusted boot and the different phases of UEFI and what's filled in different PCR registers. There's another slide here. It talks about, in the yellow circles, these are the individual PCR registers you'll see in a TPM that are updated as each of the different portions of the code are run. So when the operating system runs, there's PCR 8 that should be updated in the TPM. PCR 4 is the grub2 OS loader. The different UEFI boot services and drivers in PCR 0 and PCR 2. So that is just informational here for people interested in trusted boot. So there's a feature that, as I mentioned before, talking about secure encrypted hard drives that at least Windows is implementing today. That feature is not yet in any Linux distributions as far as I'm aware of. So for BitLocker, which is the name of their secure encrypted hard drive encryption, you can see what it's using as far as the TPM and measuring the basically the image off of the UEFI firmware, and making sure that that is measured and trusted before they transfer control to their OS boot manager and then start their OS load. So using a static root trust of measurement, this is how Windows is actually coming up and using BitLocker to boot to a secure image and a trusted boot method in their operating system if there's a TPM on the system. And then we'll talk about UEFI Secure Boot now. So in order to have UEFI Secure Boot, you need to have 3 different components. One is some authenticated variables in the NVRAM of your UEFI system. You need to have driver signing. Obviously, your images, your grub2 OS loader needs to be signed before you transfer control to it. And then there's a bunch of system-defined variables in the database that we'll talk about, the PK, the KEK, and the DB. We'll talk about those in detail here. So at build time, when you're building a secure boot system, you need to have the variables created and stored using this hash algorithm. So there's something called UEFI sign tool, and that's what some of the people from Fedora and Ubuntu have been working on. There's a GitHub project where they've created their own UEFI signing tool. Microsoft has that built into their build tools as well. So if you go up to the signing server, you can sign an UEFI driver or their OS Windows 8 runtime driver. This talks about the specific format, that the PKCS7 format that you have to use in order to sign with a private key. So obviously Microsoft has a private key for the image signing when you go up to their Windows 8 logo portal to sign the UEFI driver and any OS drivers that they have. It just talks about the steps that you go through to create the signed image that they use in Secure Boot. We talk about updating authenticated variables here in case this talks about the specific hash algorithm, SHA-256, and a 2K RSA key that they're using on the size of the key. If you are choosing to create your own variables, a lot of the things that you need to do require you to have a way of generating keys securely and to follow these specifications, the SHA-256 and X509 signature algorithm. So if you're concerned about generating your own keys, if you're going to do that, which I believe SUSE has a solution for that, you need to pay attention to this. So it's something I think Wojtek's been working on in the secure boot space. So once you have some secure authenticated variables in your system, and we'll talk about populating that in your system later on, you need to actually go through and sign your actual UEFI drivers and the OS loader itself. So Microsoft uses an AuthentiCode algorithm, which they gave up as part of their contribution to the UEFI specification. So that's coded up already up in hsiung.org, and in Secure Boot we have an authentication driver inside of all the BIOSes that will go through and authenticate your image to make sure that you're booting securely and that the signed image on the driver matches the key that you have inside the database. So at the factory, this is where the BIOS has the NVRAM basically is applied this particular key, DB key, into the database, and it's done by your OEM vendor or ODM vendor. So when they say it's Windows 8 certified or UEFI 231 Secure Boot certified, that means they're taking the key and making sure that DB key comes shipped with the key in the BIOS in the system beforehand. There's an additional requirement Windows 8 requires, saying that you have to turn off the CSM, so when you come shipping and booting in the secure boot mode, that there's no way for a legacy BIOS or any components from any malware today that uses the legacy BIOS to run. So one of the things they will check for is when they get up to the OS level that the CSM has never been run. If it has, then the system is not considered secure and will fail, and they will not certify that particular system. Also keeps you from running any of the older OSs, the legacy OSs. So we'll talk about the system variables defined in Secure Boot. So there's the PK, the platform key. So this is the key that's in the NVRAM in the BIOS in the system that enables Secure Boot, and that's specific to this your particular platform. There's the key exchange key, and that's a list of certified owners. So if you need to update the keys in DB and DBX, they have the privilege of doing that. So for SUSE, obviously there would be a CAC. Microsoft would have their own CAC. Each OS vendor typically has their own key exchange key to update their key in the system. DB is the main database, and that tells you that's the key that is populated, come shipping with the system. It tells you whether or not your signed images, your Grub2 or your OS Loader 1.8, OS Loader, etc., are allowed to run. So when you run the BIOS authenticated algorithm, this is the key that we're using to see whether or not the image is signed correctly and you go in there. So in combination with the CAC, the owner of the CAC would allow to update DB or DBX in order to tell whether or not an image is signed correctly or not when the authenticated driver is run. Then DBX is a list of revoked signers. So in the future, if there's some malware out there and somehow the signed images, the DB has been used to sign an image that is malware or has been identified to have a weakness or a hole in it, then the DBX is a list of signers, or it could be a key or it could be signed hash images of things that are known to be bad or evil, basically, or malware. So we have a good list, basically, and a bad list, DB and DBX. And then there's another variable called setup mode. So while we're obviously setting up and updating these things, you can be in setup mode where I'm populating these keys in the database, or I come with the system shipped with nothing in there, 0. PK is set up in user mode where I haven't set up anything yet, and then secure boot mode, which tells me whether or not secure boot is being enforced or not. So these are the variables that you would see inside the a system BIOS that has secure boot. You need to understand these different phases for the variables in order to figure out whether you're booting securely or not. So when you have all of these things implemented correctly in a UEFI 231 system, that's when you have secure boot enabled. So this presentation is actually an IDF presentation that one of the BIOS vendors provided. So you talk about the different steps that the people have to do in the factory, the BIOS vendor and the OEM or ODM, in order for you to populate the DB and the CAC and the BK correctly in order for you to be able to boot to Windows 8 or any other UEFI signed operating system correctly. So there's a bunch of resources here which are listed. I also have a USB key, and I've given the files to Philip to post up on a share for you to download some of these articles. They're all public articles published. There's a secure boot document up on hsiung.org and things I've collated together for you to pull down and take a look at if you're interested in implementing UEFI secure boot. So recently I invited Jeremy Kerr from Ubuntu, from Canonical, and Matthew Garrett, who's been driving most of the Secure Boot features in Linux, to come out and do a presentation at IDF. This was back in September, so it's only about a month ago. And so I wanted to include that in here. So for Linux, obviously the operating systems, the loader, grub2, and things need to catch up with obviously the UEFI 231C specification. So for Ubuntu, it's version 12.10, and Fedora, it's Fedora 18, which is, both of those are coming out here in the next couple of weeks. So they've already checked in their code and have their tools up on their GitHub tree. Unfortunately, SUSE is the last one to implement UEFI Secure Boot, and that's something that Wojtek and some other teams in SUSE are still working on right now. We're still waiting to see that implementation. We haven't seen a public implementation yet. We're very interested in seeing that. I'm in the middle of trying to cut the final label on tianocore.org for Windows 8, and I'm not really willing to do that without making sure all the Linux distributions also can boot securely as well. So we actually don't have a label up there that will pass both Windows 8 and UEFI Secure Boot with all the different distros. So I only have to wait another 2 weeks before the official Ubuntu and Fedora implementations come out. SUSE is the only one that we're really waiting on to be able to cut that final release. So I'm not sure we can wait that much longer right now. That Windows 8's already shipping, and most BIOS vendors and OEMs should have systems and BIOSes out there already in order to make their current shipment plans. From a schedule standpoint, I mean, most Ivy Bridge systems that you see from Intel will have support for UEFI Secure Boot, in this next month or two time frame. So if you go up, there's a list at the end here of motherboards that you can go purchase, and if you upgrade their BIOSes or get them, shipped with a BIOS after the October time frame, you'll see all these things turned on. You won't have any issues about getting a hold of systems like that. This is a presentation I think both Jeremy and Matt gave about a month ago, and they talk about this exact same process of populating the DB and the KEK with their grub2, signed grub2 OS loader. They've written, Peter Jones has checked in a grub2 tool for signing the OS loader image and providing there's some different schemes that they have between the different OS distributions, and we'll talk about the delta or the differences between the two different implementations. And SUSE is actually coming up with their own method here for signing third-party drivers. So I don't think we need to review. We just have gone through the basics of UEFI Secure Boot, and there's some challenges here that you have in the open source community that obviously you don't have, that Microsoft doesn't have, for since they have one company doing all of their work for generating their OS. So the problems with Linux is that you want to be able to take any Windows 8 or system set up for UEFI Secure Boot and be able to install Ubuntu or Fedora or some Linux distribution on there. So it requires that there must be some way for the user to identify, if you still want to support Secure Boot, to identify and trust a new DB or a new value that we're going to be able to boot to. So for Ubuntu, they have a way at OS runtime of populating their particular loader and their image in a system. So they've decided to take their their bootloader. They have something called a boot shim loader, which is a version of a bootloader that all it does is going to run their grub2. So they're going to have the boot shim loader signed by Microsoft with the UEFI CA services, and then on their distribution, which is actually out already, 12.10 came out last week, you can then boot securely to their boot shim loader, which will then load grub2, and then it'll execute their Linux kernel, which is not signed. So they're breaking the chain of trust between execute surfaces before UEFI exits, basically, where they're not going to check the Linux kernel to see if it's signed correctly. So their grub2 will just simply execute anything that comes after that's been installed on the hard drive. The only thing we're checking between the firmware and the boot shim loader is that the boot shim is signed correctly, and it comes from Ubuntu or from their 12.10 distribution that's been signed by Microsoft, or the UEFI CA. That's the cert that you see here on the bottom of the screen. So the Ubuntu implementation is sort of punting as far as maintaining the chain of trust, and their bootloader is not going to check their kernel to see whether or not it's been signed or not. So that's their Ubuntu certification. You can go to their signing tool site. Their tools will run at OS runtime, so you can actually sign images up at the OS runtime within a Linux distribution. You don't need to use Windows or anything to run or sign their images. So there's a demonstration they had made of this at IDF, where they took a notebook and ran this on a system and showed everybody. So as I mentioned before, 12.10 has shipped out as of last week, and you can now download this off the Ubuntu website in the past couple of days. So for Fedora 18, they have a slightly different implementation, and that's due out in the next week or so, first week in November. I think they got moved back a little bit. The delta here is that they'll also support IPv6 PXE boot as well as booting off of a storage device, but they're going to maintain that chain of trust. And the difference is they will also have a shim loader signed by Microsoft. It's going to load their grub2 loader, but the difference is their kernel will be signed, and they're separating all of their kernel drivers from the actual kernel itself. So they're going to have their own keys and their own kernel, which will have a different signature than the key that they're using for signing the bootloader, which is the Microsoft UEFI CA from the Microsoft website. So they're maintaining this chain of trust and making sure that their kernel is signed and that they maintain that chain of trust. So there's a difference there in how the two different distributions are choosing to implement UEFI Secure Boot. The third implementation, of course, is SUSE. So Wojtek has come up with an additional model of if you have third-party drivers, how are you able to get those drivers in there? And if you choose to build your own kernel, how do you get additional keys into the system, into DB, so that you can boot securely? So Wojtek has come up with a scheme where there's an MOK list, which will allow you to get an additional KET keys into the system, so that if you choose to build your own kernel and your own third-party drivers, you have a way of getting those keys into the system, in addition to running a signed image of grub2, which is in this MOK list, that you can also sign your own kernels and run not just your SUSE signed kernels, but additional kernels that you choose to build on your own, and any third-party drivers as well. So we're waiting to see, obviously, this implementation. This MOK list is being stored in something called the EFI boot services variable, so we're waiting to see how this is going to work out, and waiting for an implementation of SUSE to see if this actually works, and test this out with the actual firmware that we've released on tianocore.org, and all the BIOS vendors are obviously have systems that are available to do this. So there's call to action here. There's for the versions of Ubuntu and Fedora, you can go take a look at their websites to see what they've done before. And there's obviously some other links here that you can go to for their secure boot tags. And of course, there's the SUSE blog, which is where Wojtek's been disclosing all of the plans for SUSE and how they're going to do the secure boot with the MOK list. If you're looking to actually go off and try this out, I've supplied most of the Linux distros with at least 2 of these systems. So the main validation teams at all the Linux distros have this. Anybody can go to Northwest Hard Drives. There's a location here at tunnelmountain.net that you can go and purchase one of these DQ57 TM systems, which has a matching version of the UEFI 231C tianocore.org firmware on there, and it boots class 2 version C that I mentioned before, and you can try out your UEFI secure boot on there and see if it works. This is meant as a software development vehicle for all of the OS vendors to go off and get their UEFI secure boot or just UEFI implementations tested out and working. I'm also coming out with a server which I've supplied to the Nuremberg SUSE facilities already, and there's a future version of the Ivy Bridge Mile Bay, which is coming out soon here at the end of the year, which will be available as well. You should be able to get that system commercially from just any Intel website or channel distributor. So there's a website that we have for updated firmware images if you need to flash update the systems at UEFI DK, and there's a bunch of collateral you'll see up there to be able to boot or to be able to read all these specifications and tools and utilities for developers to go off and write their OS loaders or utilities for deploying UEFI secure boot or just UEFI in general. So there's some call to actions here for systems that you want to see booting with UEFI Secure Boot. There's a bunch of Intel commercial motherboards coming out. Any of the Ivy Bridge systems from Intel, the 77 series motherboards will have, obviously will be Windows 8 certified. You should see those BIOSes coming out here and those systems coming out at the end of the year. Or if they say they're Windows 8 certified, if they're shipped to you that way, they'll have all this stuff turned on for you. If you have an Intel Ivy Bridge Ultrabook that's touch enabled, you should see that's Windows 8 certified. You should see all these things enabled, and you can contact your your favorite BIOS ODM or a vendor to get a BIOS if you're interested in playing with that, or just buy that commercially. There's some instructions here on how you're able to tell what version of UEFI you're on. If you can get up to the shell, you can type in a ver to identify which version of UEFI, just to make sure you have the right version. And the Ubuntu, or the Canonical team, has been taken over one of the Linux firmware test suite tests. So there's the UEFI SCTs, but they don't necessarily test the functionality of UEFI. They're just there as an existence proof to see whether or not you have the correct UEFI protocols and services. So Linux, the Canonical team has taken upon themselves to write the equivalent to the Windows 8 logo tests for Linux. So there's a bunch of people working on a future Launchpad version. It's not out yet, but it's supposed to come out at this same time they launched 12.10, the firmware test suite, to test the firmware to see if it's UEFI compliant or not. So for SUSE, I was hoping there'd be either some sort of contribution or your own sort of test to figure out whether or not the firmware is compliant or will work with OpenSUSE or SUSE. So there's a call to action there. And if you find any bugs in the UEFI implementation, you should be talking to your BIOS vendor, or if it's a core issue with the actual TNOcore.org, there's a mailing list, and you obviously we want to find out about the bugs right away before someone else does, the malware crowd basically. So there's a bunch of collateral that I have and links here you can go to. My email address here. There's a few other TMEs from Intel that support UEFI that you can talk to as well, and there's some training materials. We're in the middle of moving a lot of our training material to online utilities, so there's a list down here, some URLs that if you get this presentation you can go to those links. I have some of these books in PDF format on my system here, so if you come to me afterwards, I'll be in the wharf room tomorrow. I can come by and give you those materials on a USB stick. You can just download those. Those are quite large, 30 or 40 megabytes, so I think there's a zip file that Philip has of these items as well. So if there's any questions, now's the time, or you can come by, since I guess it's pretty late today, you can come by and ask me any questions. I'll be over in the wharf room as scheduled in tomorrow. So, are there any questions on this part of the presentation? So everybody's asleep already.
About signing, why are the other distros buying their stuff from Microsoft, not from? Well, I mean, for example, there's no competitor choice.
So the question was why is everybody going to Microsoft to sign their UEFI CA images? There's a certain amount of liability associated with being the signing server or the signing association. Originally, the UEFI org was asked to provide the signing services, and the board of the UEFI org had decided based on liability. You have to decide on whether you're willing to sign an image or not, right? So there was the legal recommendation from the UEFI org, from their lawyers, saying that to not provide that service. So Microsoft stepped up as one of the UEFI members and said they would provide that signing service. There's nobody from the Linux or any other communities that wanted to provide that signing service because it requires you to obviously go out and go get a VeriSign key and provide that signing service. So had someone else stepped up to provide that service, we would have another signing server from somebody to do that. They're just hosting the UEFI CA, that key, the key which they had generated from, or we had gotten from VeriSign, basically. Right? So that private key is obviously held securely by Microsoft in a secure facility. It was generated by obviously a crypto grade device, that sort of thing. So for the OEMs that are FIPS require, they may not choose to use the UEFI CA requirement if they're trying to boot to their own signed images. If they want to sign the OS loader themselves for a Linux distro or anything else, and they're fully capable and willing. Anybody can actually do that if they're willing to sign all their own images. You have to obviously have your own signing tool in order to do that and sign both the BIOS images, the EFI drivers, and your OS loader, right? So, for your question as to why Linux vendor would want to go to Microsoft, nobody has been willing to step up and provide the signing services is really what it comes down to.
So signing from Microsoft obviously is hardwired into on the motherboard, right?
That's correct. So all the PK, when your system says it's Windows 8 certified, all the BIOS vendors, no ODMs, no OEMs, they're shipping with it's a UEFI CA key, right? But hosted by Microsoft. In other words, they have the signing tool that will allow you to sign that with the private key that they're hosting for the UEFI org, basically. That doesn't mean to say you can't get additional keys into the PK, right? There's ways of, if you talk to the OEM vendor and you provide, say SUSE wants to provide a key, that you could provide a key. The Linux Foundation made an announcement earlier that they are signing an image and providing a loader image that they're going to provide. There's nothing stopping anybody from hosting and providing keys and providing them to the OEMs and BIOS vendors and ODMs, just nobody has. So the question was, what happens if Microsoft decides to revoke the keys? And so keeps them from revoking the images. So Microsoft has an interest in, well, I can't really speak for them, but I mean, in general, speaking from the UEFI standpoint, making sure that nobody wants to see malware, transmitted, right? So the only reason why you'd revoke a key or a hash image, right, is if someone intentionally had signed an OS loader or something with the intention, obviously, of causing malware to run, right? That's the whole point. Having secure boot is that you want to run only what you installed in the system and something that was unintentional, right? So the revocation policy is not public as to, you have to, a distro or somebody would have to go to Microsoft and ask them to revoke the UEFI CA key, and consequently all images then would need to be updated, and the DBX would have to be filled with obviously that key or the hash images, right? And that's not a public disclosure right now, so that's a discussion you'd have to have with Microsoft, right? So the UEFI is comfortable. The board is obviously comfortable with having Microsoft because remember their OS is signed with the same key, right? So and their loader is signed with the exact same thing. All of the drivers necessary to boot the operating system are signed with that key, right? So you're talking about every single driver that Microsoft is trying to use out in the PC ecosystem, would have to be re-signed again, and DBX would have to be populated with the revoked key in order for you to exclude those bad images or bad things from running out there. The KEC holder, basically, right? Or I'm sorry, the PK owner is allowed to, obviously, the person with the platform key can then provide an updated image for the PK, or for the DB, right? So PK is the platform key owner. KEC is the key exchange key owner, right? So you won't accept updates to the DBX unless you've been signed by the KEC, and that's what the key exchange key is for. So both DB and DBX are updated by whoever is signed by the KEK owner.
Well, okay, but what happens if the key is compromised? Does that mean I can control all my servers?
So that is why one of the presentations included there, Microsoft talks about is generating a key. In the earlier part of the presentation, it talks about the security of the private key, right? So I'm sure, because remember, Windows is signed with this key, right? That they have,
Well, no, but there are billions of machines in the world which use that key. Well, then there is a big motivation to try
Right, which is why, right. So the other thing that Microsoft has provided, right, is remember every Tuesday of every month, right, there's a security update. One of the things they're able to do is obviously update the key, the DB key, obviously through a security update. One of the things that we're working on with Microsoft is something called capsule update. In addition to just, suppose there's a bug in the Authenticode algorithm is found in itself, or I need to update part of the BIOS, which is checking the hash, right? They're providing a way of actually updating both the firmware and the DB key so that automatically systems just who have Windows security update included and turned on in their systems would automatically be able to update the systems, and if they need to issue a new DB and a new DBX, obviously, right, they can do that out in the field. So that was the attractiveness of using this UEFI security boot model, was they have a way of doing that, right? And this would benefit all of the distributions, not just obviously Windows. I mean, it's anybody who's signed with that key, right? They have as much interest in anybody else in seeing that only what's signed is run and not something else unintentionally running around out there. Right?
Who provides the device driver?
So that's the weak point. So the question was, who provides the device drivers for UEFI? It's the system providers, and that's obviously that's Intel for our own chipset, for our Southbridge, the SATA controller. It's part of the BIOS, right? If you have a plug-in card, now it's, for example, Broadcom for network cards, LSI for their RAID cards, ATI or AMD ATI or NVIDIA, right? So each vendor needs to provide a UEFI signed driver. Typically they're signed through the same, since they need to provide a Windows 8 driver, typically it's the exact same place they go to sign their OS runtime Windows 8 driver. So at the same time they can get their UEFI driver signed in the same portal and get their card signed and then provide that services. So Philip was, as indicating, discussing with me, some of those device vendors do not have UEFI drivers, much less UEFI signed drivers available, right? So that's probably the weakest link in this whole thing right now, is providing third-party drivers. And that's something that everybody is looking to SUSE to provide, is a way for the ability for third-party vendors to sign their drivers dynamically and be allowed to run basically in a UEFI secure boot system.
Yeah, to clarify, UEFI drivers to the current spec needed for
2.3.1c, right.
Will barriers exist, either monetary or policy-wise, in obtaining the sign?
You can, the question was, what are the barriers for getting your own sign key? You can go to VeriSign and purchase your own key from them, or Microsoft would also provide a key. I believe it was $99 is what they were saying. I mean, that's not exactly prohibitive in any way, but that's the only financial barrier that is there. They have their own yes, they have their own policies in general, right? Just like VeriSign has in verifying who you are. They have certain requirements. You have to talk to them what those are. I mean, I don't have those requirements with me or at hand.
And Microsoft pointed out that the cost associated with VeriSign,
they're just providing the signing server, basically.
Does Microsoft have an obligation to issue?
I'm sorry.
If I say SMS or whatever, fulfill all the steps to get my thing signed, does Microsoft then have an obligation to sign it?
I think you'd have to talk to Microsoft. You're talking about signing it with the Microsoft, the UEFI CA key, or you're talking about your own key?
Yeah.
No. So you need to understand, with the signing tool that the Linux community has already provided, you don't need to go to Microsoft anymore to get the key to sign an image once you have your own. If you're talking about, if it's not the UEFI CA, you have your own key that you're signing. You don't need Microsoft or their signing services, right? If you have your own key, you've gone to VeriSign, you've gotten your own key, through a secure source, a crypto source, right? And you're going to use the Linux utility in a Linux operating system to go sign using that signing tool, right? Then you don't need Microsoft in that case. So there's no obligation on their part, right? Because you don't need them. So it's only when you need to sign something using the UEFI CA key, that's where you need to go to their signing service, their CA services. Any other questions? Okay. Like I said, I'll be around all day tomorrow, Wharf in the other room, so if you need to stop by and want any of these materials, you can stop by and I can give you a USB stick with the thing, or you can download it from that URL.